Thank you. Right. There we go. Cool. So you're asking about assignment 1, do we include, apparently the year 1900 wasn't a leap year. I'm not talking about what leap years were existing historically, I'm talking about what is the rule for leap years. There we go. Cool. Yes. And no, I would prefer to still do this on YouTube. So there you go. Cool. Anyway, that's what we're doing, and there you go. So let's continue with our our stuff that we were doing in the lecture notes. So the last time that we were talking, we covered a fair amount of material actually. We talked about the call stack. We introduced libraries and how they work, and we also talked about a little bit about variables. So let's get into things a little more in depth. We had already talked about the difference between passing by reference and passing by value. Passing by reference, you're passing a pointer to the thing that you're trying to pass instead of passing the actual physical value of the thing that you're trying to pass. Let me just... Yep, my microphone's on. There we go. Some languages pass by reference by default for everything. These include this includes Perl, VB, and Visual Basic, and Fortran. Most of the major languages pass by value. This includes C, Java, and Python. In C, you can pass by reference, but you are passing the value of an explicit reference, so it's slightly different than you might expect. But yeah, so let's see. Cool. Cool. So, in C, one of the fun things that you can do is you can create your own customized data types with an asterisk. It's not, well, C gives you enough expressive power to be able to create some pretty complicated data types once we start getting into structs. However, what we're talking about right now is more like a type synonym. So let's say you wanted to define some custom data type name, and you wanted to say, like, for example, every time you type byte into your C code, you want that to mean 8 bits. Well, we know that unsigned chars are 8 bits in length. So we can define the type using typedef. Typedef unsigned char is byte. So it's like this is a synonym. This is a synonym for that. Byte is a synonym for unsigned char. After this typedef in your code, you may use byte anywhere you want to use some type of... you can use byte anywhere you would use a type specification. So when you're initializing a variable, you can use it. When you're specifying the inputs or outputs to functions, you can use it. And that's the major ones for now, I think. So the way that this works under the hood is that the compiler swaps out whatever type synonyms you've assigned at compile time. So it's not like your new type label is actually going into the compiler itself. It's getting swapped out for what that means. So you might say to yourself, okay, so I can create synonyms for things. Why would I want to ever do that? What is the possible point of this? And the answer to that is you can assign specific names to specific data types in order to increase the readability of your code. So you could imagine a situation where if you had, you know, let's imagine that you were trying to process data packets, and the header for the data packet was always X number of bytes. You could create a structure that contains all of the things that are in that data packet, and each of the things in the data packet can say what they are. So, header H or whatever, data byte B or whatever. And if you have the type defs assigned for that, then it's much easier to read and much easier to understand what you're on about. You may notice that a certain amount of this C programming stuff that we're learning is specifically geared towards trying to write programs that are legible. And that's not by accident. Because of the nature of C as a programming language, and its inclusion of things like gotos, and like C is intended by its designers to be one step up from an assembly language. So it is super, super possible to write code that is completely impenetrable to human examination. If you write code like that, nobody will thank you, not even yourself. So a lot of these sorts of conventions are things that are useful for you to know, and even more useful for you to abide by. So there you go. Let's see. Cool. So there you go. You can define your own types. Enumerations are a little bit more fancy. They do a little bit more. They're still a type. So when you define an enumeration, you are defining a new data type. The difference here is, when you define this new data type, you are also defining a bunch of literals that go with that data type. So, for example, we have this enumeration declaration right now. Enum, Pokemon status, you have faint, sleep, paralysis, poison, freeze, burn, and none. Each one of these is a literal value that can be assigned to the type Pokemon status. So this is, this can be very, very useful for, making your code more clear. For example, this code right here, it's pretty obvious what it's doing. We are declaring a status, initializing it to none. If the status is poison, then HP equals HP minus HP divided by 16. If the HP is less than or equal to 0, then stat is equal to FNT. It just makes the code much, much, much more legible. And, yeah. Boop. Boop. So yeah, that's essentially the gist of enumerations. You might be wondering, okay, so we have these literals, but what is it actually doing? How's the compiler dealing with these? Is it something like in something like Python, the inclination would be to store these as strings rather than to create an enumeration for them. Although I'll be very surprised. I would be very surprised if Python didn't have support for enumerations. So, in reality, each one of these is mapped to a literal bit value. And you can actually expose what these bit values are by printing them as integers. So, if we were to take this program, copy that, do I have the code in here? Perhaps not. that is terrible. All right. Well, at any rate, easy enough to reproduce. Incidentally, the convention for data types and enumeration literals is to have them capitalized. GCC, W all. I know it didn't end up being about Pokemon, but you know. There you go. PKMN. So you can see the literals that are being assigned to these enumeration, the bit interpretations of these enumeration literals are literally just 0, 1, 2, and it just assigns sequential bit values to each of these enumerations as you go up. So the implication there is that you can perform, for example, equality tests on integers, although generally speaking, you should try to stick inside of the context of using the enumeration literals. You know, it's you can use casting, of course, but you know, it just keeps it a little more clean. Boop. There we go. So, just like type defs, the main purpose of enumeration is code readability. So, again, you can imagine how much worse this code would look if this was an int. You know, this was, 7, that was 2, that was 5, etc., etc. There's no way of imparting, like, semantic content for a human reader with just numbers. It's like, unless you have some table somewhere that you've put in the comments, 7 means poisoned, 3 means burned, etc., etc., and you just list that out and, put that documentation in there somewhere, someone else is going to have no idea what these numbers that you're doing all these equality comparisons against are actually doing. So if you're going to go to the effort of putting comments into your code that say, by 1 I mean this, by 2 I mean that, you might as well just encode it as an enumeration and have that straight in the source code itself. But that's how you do enumerations. Boink. Don't be a dope, consider the scope. The scope of an identifier denotes what parts of the program that identifier is accessible in. For you guys who are in the chat, you guys have done scoping a little bit, I hope? Yes, comparing enumerations with integers works. Comparing integers with characters also works, because when C says equality, what it means is I am comparing the bits. That's how C works. So you guys have done scoping a little bit? Hopefully. there are specific ways that things work inside of C, so let's talk about it. So, levels of scope are often called contexts or namespaces. These are important terms. Cool. We are often taught that scopes can be local or global, depending on whether the identifier is available only within a particular function or throughout the whole program. That's the difference between local and global. That's kind of the first year way to talk about scope, though. You guys are in second year now, so you need to level up your concept of what scope actually means. Because it's not just based on the grammar of the programming language. There's an actual reason for it. Yeah, so if you're deciding what the scope is by looking at the program and saying, oh, that's inside the function, that's basing your knowledge of the scope on the grammar of the program. We tell that by looking at the program's structure. Incidentally, the public and private objects of object-oriented are a related concept, but they're distinct. A better way to think about scope is to think about how the call stack works. So, the top-level frame in the call stack is the local context for the program that's currently being executed, and functions, in this context, are considered programs. You can think of that as the most local context. So, you can, when you think of, instead of thinking about a sort of binary division between local and global, locally scoped and globally scoped variables, I want you to shift gears in your thinking and think about levels of locality. So, if you're running a function, the variables that are in that function are the most local variables. If that function has been called from main, the variables in main are the next local. They are a less local context. So think about it in terms of like more or less global and more or less local. So the most global context in this case would be something like your operating system's kernel. The variables, basically the idea is you can look down the stack at variables, but you can't look up the stack at variables. And the reason for that is where program execution is stuck. While you're executing a function, that function has control over the program pointer, right? So it's not necessarily that the variables that are local to the function don't exist in the global context. It's more like the global context will not be capable of executing anything while the function is executing. So while those variables are existing, hypothetically, if you could execute code that was further down the stack, that code could, in theory, look up and see, the stuff above it. But because the execution is stuck in the most local stack frame, until that function terminates and then the stack frame is closed, the local variables are deleted before the less local context has the chance to try to look for them. So hopefully that makes a certain amount of sense. Yeah. The reason local variables are not accessible in more global contexts is because they are deallocated before program control is returned to the calling program. This is why local contexts can access less local contexts, but not vice versa. So there you go. So, we have another concept that we have some constructs, some syntactic constructs in C, which allow us to modify where a variable is stored and therefore the context in which it's accessible. So, generally speaking, well, let's go through what the four are first. We've got automatic variables, or auto. We've got register variables, external variables, and static variables. So, automatic variables are the variables you've been using so far. They are stored in the stack. They are initially populated with garbage data. They are scoped to the block in which they occur, or the function they occur in, and they are deallocated or deleted or removed from existence when you reach the end of that block, and block here, of course, meaning function, or program. So, automatic variables are the variables that you know and love. You can actually explicitly declare a variable as being an automatic variable using the auto keyword. You just, rather than write, int I equals 0, you would write auto int I equals 0. There you go. Generally speaking, there's not much call to actually do this, as auto is implicit whenever you create it. Whenever you create a variable, auto is assumed. So you don't really need to use the keyword very often. This is variables as you know them. External variables are stored in the data segment and not the stack. So because they're not stored inside of the stack frame, then they are persistent between execution, or between different functions executions. Rather than being initially filled with garbage data, external variables are given, the memory is wiped before it's given to you. Of course, this means that it takes a little bit more time to actually allocate you an external variable. The computer goes to the trouble of wiping it for you first. The scoping of this, of an external variable, can be multiple files, multiple programs. It's in a more global context. So, because it's outside of the stack, right? So, in this case, because it's not in the stack itself, it's not subject to that sort of less local, more global idea of locality. So you sort of put it off to the side and you can access it separately. External variables are deallocated when the program that created them is terminated. Static variables are very similar to external variables. However, you get it's like a combination of external and auto. Oh, yeah. Yes, I already... Yeah, okay. One more note about external variables. If you're declaring... If you declare a variable outside of any function in a C file, then the extern keyword is there by default. So that is assumed to be an external variable. However, if you wanted to declare something in here as being a global variable, then you use the extern keyword, and that sort of pops it out into the global context. There we go. Questions? Okay. bum, bum, bum. So static variables combine the persistence of an external variable with the visibility rules of an automatic variable. So if you were to declare a static variable inside of a function, that the value that that variable has is persistent between function calls. So it would be a cool, this would be the way, for example, if you wanted a variable keeping track of the number of times a particular function has been called. You could have a counter that increments every time the function executes and assign those values to a static variable. The static variable is stored outside the stack. It is, again, given a 0 value. In that way, it's like an external variable, and it maintains the persistence while keeping the locality. And finally, we have the odd duck. We have register. You can actually tell C that you would like to use one of the CPU's registers directly as memory. So if you remember the way we were talking about the different types of memory back a few lectures ago, I think a couple of weeks ago even, we specified that there's a difference between data storage in ROM, in RAM, and in registers. Registers are the most fast. However, there's a very limited number of them. In C, we can say, okay, we would like this variable to be stored in a register. Because it's stored in a register, operations occur on it very, very quickly because it doesn't have to be loaded and unloaded from the RAM before it's worked on. The stack is stored in RAM, by the way. It has garbage values for your initial value, and it is scoped the same way as an automatic variable. In a lot of ways, it is an automatic variable. You're just telling C where you would like it. Now, the trick with that is that the compiler does have the right to say no. You should think of designating a variable as a register variable. You should think of that as a suggestion to the compiler rather than a command. If the compiler just simply does not have those registers to allocate to you, then, that's the situation you deal with. Incidentally, the compiler will actually assign a bunch of your variables to register variables if you decide to use one of the optimization flags. So optimization flags allow basically you're saying to the compiler, okay, I have written a program. Why don't you see what you can do to optimize it, in GCC at least. And one of the things that GCC will do in order to optimize your code is to see which of your variables are used frequently, and if they're used frequently, they would be probably better put in registers. So there we go. We have a question. Can I give an example of when we would need to use a register? Well, you never need to use one. It's kind of like how you never need to use an enumeration. You can always get around using one, right? It's more if you'd like to play around with seeing if you can get your program to execute faster, then human intelligence is superior to machine intelligence. That's sort of the general design philosophy of C. The general design philosophy of C is, since human intelligence is better than machine intelligence, we are going to give the human all of the tools that they need to optimize their code to the same degree that the machine would be able to, and assume that the human being can exceed the optimizations possible by the machine with human cleverness. So, if you wish to try optimizing your code beyond the level at which it can be optimized by GCC's automatic processes, then you can try assigning some of your variables as register variables. But yeah, it's like, you're not required to do it. Like, you're technically not required to, what else are you not required to do? You're not required, technically, to use functions, unless, your assignment says write a function to do X. You can put all of the, you can write out your entire program in terms of, like, you can take anything that you were going to put in the functions and insert it manually where the function call would be. You can just put the code in there. You can do that manually. It doesn't mean it's a good idea, but, yeah. Anyway, hopefully that's an answer to your question. So, rather than continue to talk about variables, let's talk about recursion. So, my understanding is that you guys have touched on recursion, but never really gone through it in a lot of depth. Recursion is not intended to be a major topic of this course. However, it is going to be necessary for you guys to have some idea of recursion and recursive processes and algorithms in order to get some of the data structure stuff that's coming up. In particular, like the quicksort algorithm is very much a recursive algorithm. So we're going to talk about recursion at, 14 minutes to the bell on a Friday. Okay. Cool. So, if you already know what recursion is, just remember the answer. Otherwise, find someone who is standing closer to Douglas Hofstadter than you are and ask him or her what recursion is. And the idea is, if everybody followed this, then eventually someone would be Douglas Hofstadter, they would give you the answer, and then that would be passed back the chain to the person who was asking the question. So, recursive algorithms are a class of methods of solving a problem where the solution depends on solutions to smaller instances of the same problem. So the idea is, with recursion, you have a problem, you take a chunk off of it, and then you apply the same strategy to the reduced problem. So this is particularly effective on problems that can be defined inductively, inductive definitions. A couple of inductive definitions that you're probably familiar with are factorial and most particularly the Fibonacci sequence. So in factorial, n factorial is defined as n times n minus 1 factorial. So the way that you would write a recursive algorithm to solve n factorial is you would multiply n by the result of n minus 1 factorial. You would call the factorial function again, passing it n minus 1, and then that would compute and compute and compute until it hit 1, and then it would stop, pass the results all out the way back up the chain, and eventually that would return to n factorial. Question. External variables are not read-only. You can edit them. The Fibonacci sequence is another classic example of a recursive algorithm. And it's a little bit more intuitive, I think, than factorial, because, like, very specifically in the definition of the Fibonacci, like, the definition of the Fibonacci sequence is that any element of the sequence is the sum of the previous two elements of the sequence. And that's what this expresses. For a Fibonacci of n, if n is greater than 2, then it's equal to the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. However, if n is equal to 1 or n is equal to 2, this is or in formal logic, by the way, then it's 1. And that's, again, embedded in the definition of the Fibonacci sequence that you probably already know. The first two numbers are 1. So, fundamentally, the sort of most basic definition of a recursive function is a recursive function is any function which calls itself. So, recursive functions generally have an iterative case and a base case. The iterative case makes a decision or performs an operation, or in some way modifies the data passed into the function and calls the function again with modified inputs. The inputs of subsequent function calls should travel in the direction of the base case. So, for example, in Fibonacci, this is the iterative case. We need... The iterative case is the one that contains the function calling itself. That operation is in the iterative case. The base case does not require the function to call itself to return a value. So the problem with a recursive function is if you make the recursive function always call itself, then it will never terminate. It will never finish. Because every time you try to find the answer to, some set of inputs, you're going to invoke another function call, and that will happen every time, which means you'll never finish. However, the idea is that eventually you hit a case where you don't need to call the function again. And when that happens, you have an actual concrete value that does not require another function call. That can just be passed up the chain. That'll be used to evaluate the thing that invoked that. That'll produce a solid result. That solid result will be passed up the chain, and the solid results will just be passed up the chain forever until, well, not forever, until it hits the thing that called the function to begin with. Question. If a recursive function calls itself, wouldn't you get an infinite loop? I think that you might be I think we're hitting the being slightly behind, like the 30 seconds behind problem. When you have a base case, you're not going to be calling yourself forever, because you're not calling, like, the function calls itself in a specific situation, and it does not call itself in other situations. So, you may be interested to know that some programming languages, like Haskell, use recursion exclusively. There's actually no ability to write a loop in Haskell. Everything is done with recursion, which is kind of interesting and fun. And of course, Haskell has been specifically designed so that that is efficient. So here are some recursive functions that relate to the recursive algorithms that we spoke about on the previous slide. With respect to factorial, if n is equal to 0, then we return 1. Otherwise, we return n times factorial of n minus 1. So, you can imagine... So, this is my replacement for a chalkboard right now, right here. So if we have, I'm just going to call it f. If we have factorial of 5, then I'm going to split screen this. Ho ho. There we go. So if we want to evaluate what factorial of 5 is 5 equal to 0? No. Then we return this value. So this is equal to 5 times factorial of n minus 1, which is, of course, evaluated to 4. The next step is the computer's like, oh, I need to know what factorial of 4 is. So the return so factorial of 4 I'm going to use tabs. There. Factorial of 4 is 4 times factorial of 3. Factorial of 3 is 3 times factorial of 2. Factorial of 2 is 2. I know it's kind of messy, but, times factorial of 1. And the value of factorial of 1 is 1 times the factorial of 0. Now we've hit the base case, right? When we try to execute factorial of 0, up to this point we've been hitting this else branch the entire time. But because this is 0 now, that has a concrete value of 1. So the concrete value here is 1. That means that f at 0 gets replaced with 1. 1 times 1 is evaluated, it's 1, and that is passed back to the invocation of factorial of 1. 1 times 2 is 2. That's substituted for f2. This is evaluated. That's 6. 6 is replaced with f at 3. This expression is evaluated. 24. 24 is substituted for f4, and that 5 times 24 is evaluated at 120, and when 120 is passed back to the factorial function as the calculated value of the factorial. That is that's the actual I apologize that I don't have a chalkboard, because it would have been more clear with a chalkboard, but that is how the factorial is computed using this recursive algorithm. Hopefully that's reasonably clear. So let's do the other one, Fibonacci. Notice if n is equal to 0 or 1, return 1. Else return Fibonacci n minus 1, n minus 2. So let's do something easy, like let's call it, I'm going to call it f again, but Fibonacci of 4. So Fibonacci of 4 is Fibonacci of 3 plus Fibonacci of 2. Fibonacci of 3 is Fibonacci of 2 plus Fibonacci of 1. Fibonacci of 2 is Fibonacci of 1 plus Fibonacci of 0. Now, we know that these invocations here, f1, f1, and f0, those are all going to be returning 1. So we can substitute, so those will be substituted for 1. f2, however, again, this invokes the else case on the recursive function. So that's going to be f1 plus f0. And, in terms of the actual computer, it would probably do these in the order in which they occur in the expression, but, it is what it is. So these guys will be substituted for 1s. That will be evaluated to 5. 5 will be given as the result of f4. So that's that's how that recursive function would work. Notice that this one, with this one, the number of calls to the function is expanding rapidly, because each time we execute the function, we are creating 2 more instances of the function. We're creating 2 new function calls instead of just 1. This can be a huge problem if you're for large numbers. So we have a good question: how deep can recursions go in C? And that's actually related to the next slide. So I'll just do the next slide. In C, all of our function calls go straight onto the system call stack, as opposed to Haskell, which handles things differently. So if you remember what we said about the call stack has a fixed size. It can only accommodate so many function calls. So if the recursion depth is too great, you can easily cause a stack overflow. So the number of recursive function calls you have available to you is the amount of your system call stack that you have remaining. The algorithm Fibonacci here will run through the system call stack very, very quickly. So factorial creates 1 function call per, whatever the value of n is, that's the number of function calls that you'll have to do, like plus or minus 1 or 2 or whatever. However, the number of function calls that you'll need to do for Fibonacci is 2 to the power of n. So you can see how as n increases, the number of function calls that you will need to have to compute Fibonacci is exceptionally large. Now, there are ways of getting around this. One of these is called Memoization, but we're not going to talk about that today, or probably in this course. Just be aware that if things are calling themselves twice, that blows up real fast. Everything a loop can do, recursion can do, and vice versa. So Fibonacci could have been computed using a loop, and so could have recursion, or so could have the factorial. I know I'm just about finished. So recursion is an option. It's not like some algorithms will be expressed much, much more succinctly if you use a recursive solution. However, a looping solution is always possible. And the same goes for looping solutions. Looping, it might be easier to express a program as a loop, but you could always do a recursion instead. So, many useful data structures have recursive definitions, such as trees, heaps, lists, and linked lists. Some of these things are things we're going to talk about in this course. Some of these things are going to be things you talk about in the algorithms course that you guys have coming up next semester. We'll eventually get to these when we learn about structs. There we go. So, this is the last slide comic. I can't believe that we actually have, we are just about exactly on time in terms of, the slides being matched up to the weeks that they're supposed to be covered in. So let me see what this question is, and concerning the assignment, should you keep POW or use the for loop? You can either use a loop to do POW, or you can use POW. Just because POW isn't working in Jupyter does not mean it's ineligible as a solution. We're working on the autograder issues. For now, just write a program that works in VS Code or Bash, and that will be, if it works there, it'll be marked as correct for the solution. Once again, our primary criteria for whether or not a solution to a problem on an assignment or a test is correct is, does this program work? We're evaluating your solutions in terms of, if we give you these inputs, do you produce the expected output? So, we're not marking stylistically necessarily, unless if the question says in it specifically you're going to get marked on style for this one, then there will be a certain number of points allocated to style, and the number of points allocated to style will be specified. But, you know, that's how the assignments are going to be marked. But yeah, so looks like some variable names work, including yes. So it turns out that according to GCC, the $sign character is a valid identifier character. However, this is not in the C standard and is not universally true among C programs or C compilers. So, if you want your code to be portable to other C compilers, then you should not include $sign in your variable names. However, there you go. I'll let you guys come to whatever conclusion you like about whether that makes it a correct or incorrect answer on the assignment. But yeah, if there are no other questions, I'll keep this chat up for a little bit. So if you, I'm going to leave it to you to decide whether it's a good idea to name your variables after the function that is main. You should be able to figure that one out. I'll keep this chat up for a little bit longer to answer any questions that you guys may have, but otherwise, I think it's time for lunch! And also have a good weekend. Have a good weekend, everybody. I hope that you have a good one. Take her easy, folks.